Okay, so here's where we were, and I was about to write in the answer, and the system just decided to go to a black screen. So we were discussing significant figures. This should come out to 6.0 times 10 to the negative 14th, and it's grams of oxygen. So that's my answer. So let's do another example. You have a sample of magnesium cyanide. It contains 34.5 grams of nitrogen. And we want to know how many grams of magnesium cyanide are in the sample. So this problem is almost the opposite of what we just looked at. We're starting with 34.5 grams of nitrogen. So we're starting with the element. And we've asked to figure out grams of magnesium cyanide. So mass, whoops, go back. So mass of the compound. So 34, let me make sure I'm not writing with my highlighter, 34.5 grams of nitrogen is where I'm starting. And I know that the only way I can get out of grams of anything is to use its molar mass. So I go to my periodic table and see that nitrogen has a molar mass of 14.01 grams per 1 mole of nitrogen. So grams of nitrogen disappear, and I have moles of nitrogen now. But I'm starting with nitrogen, but I need to get to magnesium cyanide. And if we think about it, magnesium cyanide has this formula, MgCN2. So from what we've learned here in Chapter 6, we can say that 1 mole of magnesium cyanide is equal to 2 moles of nitrogen, because there's 2 N's in 1 MgCN2. So down here I'm in moles of nitrogen, but I know that I need to get to magnesium cyanide, and this relationship that we just figured out is exactly what I want to use. So I've got my 2 moles of nitrogen to 1 mole of MgCN2. So now moles of nitrogen disappear. I'm not totally done because I asked for grams of magnesium cyanide. So again, anytime I'm in moles and I need to get to grams, I use the molar mass. So 1 mole of MgCN2. And to do this, I need to add up the molar masses of 1 magnesium, 2 carbons, and 2 nitrogens. So 1 magnesium is 24.31, and 2 carbons is going to be 24.02, and 2 nitrogens is going to be 28.02. I just multiplied those for a grand total of 76.35 grams per mole. That's my molar mass. And so then to solve this, take my 34.5, divide by 14.01, divide by 2, and multiply by 76.35, which gives me 94.0 grams MgCN2, which makes sense. If the sample contained 34.5 grams of nitrogen, then the entire sample should be larger, which my answer is, which is good. Okay. The other topic, or the way we're going to work with moles here in Chapter 6, is in chemical reactions. So first, just a basic, what is a chemical reaction? Well, we start with reactants, and then we have a chemical reaction arrow, which shows that a chemical reaction is occurring. It looks like this. And we go to products. So reactants are always shown on the left side of the reactant arrow, and products are always shown on the right side. And basically, a lot of what you'll be doing in here is balancing chemical reactions, which means you're adjusting the coefficient numbers of substances to make the total number of each element equal on both sides. And that may sound like kind of gibberish right now, so let's go and look at an example. Except now my slide doesn't want to advance. Next. Okay, so for example, sodium reacts with chlorine to produce sodium chloride. So the formula of sodium, well, first let's back up for a sec. How do we know, based on this sentence, what are the reactants and what are the products? So it says sodium reacts with chlorine. That tells me that these are the things that are being combined in the reactants. And then it says to produce sodium chloride. So sodium chloride must be in my products. So that means sodium and chlorine are on the reactant side. So I have sodium plus chlorine. Now chlorine is one of the silly seven, meaning that when it's by itself, it actually shows up as a diatomic molecule. And in case you're wondering, all of these, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine all do this. So it's 7 different elements that when they show up by themselves, show up as diatomic molecules. There's my chemical reaction arrow showing that I'm doing a chemical reaction and changing my reactants to products. And then I need to write the formula of my product, sodium chloride. We know sodium has a +1 charge, and chlorine, when it forms an ion and with a metal, is a -1 charge. So my formula is NaCl. So this is the first step, to write out the actual formulas of my reactants and the formulas of my products. Once I'm done with that, now I can assess how many of each type of atom there are on each type of the reaction. So to do that, I'm just going to list them out. On the reactant side, I have 1 sodium and 2 chlorines. On the product side, I have 1 sodium and 1 chlorine. So my objective here is to choose coefficients to put in front of each of these things so that I have an equal amount of sodium and an equal amount of chlorine on both sides, at which point then the reaction is balanced. It's not balanced right now because I don't have an equal number of chlorines. So the issue is I've got more chlorines on the reactant side than I do the product side. So that means I can adjust the coefficient of my product and increase it to 2. That changes the chlorine. It also changes the sodium, because that 2 affects everything within the compound. So now my chlorines are equal, but my sodiums are off. So I have to go back to the reactant side and put a 2 in front of the sodium, at which point I've got an equal number of sodiums and an equal number of chlorines on both sides of the reaction. I also have whole number coefficients, so no fractions. And if you'll notice, they are the lowest ratio. So it could have been that you balanced this and came up with 4 sodiums and 2 chlorines went to 4 NaCls. That's balanced. I have an equal number of each type of element on both sides of the reaction, but it's not the lowest whole number ratio because each of these can be divided out by 2. So you want to make sure that once you get it balanced, you have the lowest whole number ratio. Let's do an example, a little more difficult. We have lithium oxide reacts with strontium, I should have a with there, to produce strontium oxide and lithium. So again, what are my reactants? Well, lithium oxide reacts with strontium. So that tells me those are my reactants. My products then are going to be strontium oxide and lithium. So I need to come up with the correct formulas first and write them in the right places. So lithium oxide has the formula of Li2O. I'm reacting with strontium, not one of the silly 7, so it just shows up as a single atom, to produce strontium oxide, which has a formula of SRO, and lithium. So now I've written all of my formulas. I need to assess how much of each I have. So on the reactant side, I have 2 lithium, 1 oxygen, and 1 strontium. On the product side, I have 1 lithium, 1 oxygen, and 1 strontium. Let's scoot, there we go. So it looks more like an oxygen. So it's not balanced because my lithiums aren't balanced. So what can I do? Well, I can put a 2 in front of the lithium, which changes this to a 2, and now everybody's balanced. Let's make it a little more difficult. Calcium nitrate, which is CaNO3, 2, reacts with iron 3 sulfide, which is Fe2S3, to produce calcium sulfide and iron 3 nitrate. So hopefully you're noticing here that it's really important to be able to name and give formulas of compounds correctly. Because if you get the formula wrong, it can be really difficult to balance these correctly. So there are my correct formulas. Now I'm going to run through and figure out how much of each thing I have. And I'm also going to notice that I can take a shortcut here. Because see here, I have a nitrate, and over here I also have a nitrate. That means that when I go to balance, I can actually balance nitrates rather than individual nitrogens and oxygens, which is kind of nice. So 1 calcium, 2 nitrates on the reactant side, 2 irons, and 3 sulfurs. On the product side, 1 calcium, 3 nitrates, 1 iron, and 1 sulfur. So this is a little bit more complicated. I've got multiple things that aren't balanced. In fact, the only thing that's balanced right now is the calcium. So it doesn't actually matter where I start on this problem. Because all of these things are paired up and none of them are by themselves, I just need to pick one and start balancing. And you may find that you go to balance and you put coefficients in front of something and then you have to go back and cross them out. And that's okay. So I'm going to start with my nitrates. And I see that on one side I've got 2 and the other side I've got 3. And it's difficult to turn 2 into 3 and 3 into 2. So instead of trying to do that, I'm going to think about my lowest common multiple of 2 and 3, which is 6. And figure out coefficients so that each nitrate turns to 6. So on the reactant side, since I have 2 nitrates, I'm going to put a 3 out in front of the calcium. That changes my nitrates to 6. Changes my calcium to a 3. Over on the product side, I had 3 nitrates. Turning into 6 would require putting a 2 there. So now 6 nitrates, but my iron has been affected. In a good way, though, because now look what you see with the iron. It's been balanced. Calcium, though, is no longer balanced. So I see calcium. I have 3 calcium in the reactants. When I go and look at the products, I see 1 calcium. If I put a 3 in front, that changes my calcium to 3, and it also balances my sulfur. And then I last check to make sure that I have the lowest whole number ratios of each. I do, so this is balanced. Oh, apparently I had a page for doing that work. We can use balanced chemical reactions as kind of a chemical recipe, and the broad name for this is stoichiometry. So each balanced reaction includes multiple conversions. For example, in our sodium plus chloride reaction, going to make sodium chloride, that reaction, those coefficients here, tells me that for every 2 moles of sodium, I need 1 mole of chlorine. For every 2 moles of sodium chloride, I need 2 moles of Na, or 1 mole of chlorine. So that's 3 different unit conversions that came right out of my balanced chemical reaction. And we can do this with any balanced chemical reaction. PowerPoint does not want to cooperate here. Let's go into next. So for example, how many grams of sodium are needed to react with chlorine to produce 13.0 grams of sodium chloride? And there's some steps to this process. And the great thing about these is they're pretty much the same every single time. So step 1, write out and balance that reaction. We've already done that for this reaction several times, so we'll rewrite it on the next page. Step 2 is convert whatever you have been given to moles of the same thing. So we've been given 13.0 grams of sodium chloride. This step tells me that I'm going to want to change grams of sodium chloride to moles of sodium chloride. Step 3, I'll use the mole-to-mole conversion in the balanced reaction to convert to moles of the requested item. So the question asked me for grams of sodium. So in step 3, I'm going to change from moles of sodium chloride to moles of sodium. My final step will be converting to the desired N unit, which in this case was grams of sodium. So let's go ahead and do this. So I have, let's rewrite that equation, Na plus Cl2 goes to NaCl. And I needed 2 there and 2 there. So there's step 1. I've written out and balanced my chemical reaction. Step 2, I was given 13.0 grams of NaCl, and I need to change those to moles. So in order to do that, I need the molar mass of sodium chloride. So I go to my periodic table and add the molar mass of sodium, which is 22.99, plus the molar mass of chlorine, which is 35.45, which gives me 58.44 grams NaCl per 1 mole of NaCl. So there's step 2. I'm in moles. Step 3 was convert from moles of one thing in the reaction to moles of another thing in the reaction. In fact, I want to go to the moles of the thing that it's going to ask me for. And in our question, I was given moles of sodium chloride, and I was asked about sodium. So that means I need the coefficient ratio given in the reaction between sodium and sodium chloride. And we can see here that there's a coefficient of 2 in front of the sodium and a coefficient of 2 in front of the sodium chloride. So that tells me there are 2 moles NaCl to 2 moles Na. My last step was to convert to the desired unit, which was grams of Na. To do that, I used the molar mass of sodium by itself, which was 22.99 grams. So then put it into your calculator. 13 divided by 58.44, essentially times 2 divided by 2, which is essentially 1, times 22.99 gives me 5.11 of sodium. Let's do another one. How many molecules of oxygen are needed to react with 3.5 grams of CH4 if the reaction produces carbon dioxide and water? So step 1 is balance that reaction. Hidden within this story problem is information about who's reacting and who's being produced. It says oxygen is reacting with CH4 if the reaction produces carbon dioxide and water. So that tells me my reactants are oxygen, which is one of the silly 7, so it's diatomic, and CH4. And they are going to react together to make carbon dioxide and water. This type of reaction is called a combustion reaction because it's something reacting with oxygen to make carbon dioxide and water. A good trick for balancing these reactions is to leave oxygen till the end in terms of what you're balancing, because oxygen's all by itself. So if I can get everything else balanced, then I just am left balancing the oxygen. So let's balance. I've got 2 oxygens, 1 carbon, and 4 hydrogens on the reactant side. And I have 3 oxygens. Notice there's 2 in the carbon dioxide and 1 in the water. 1 carbon and 2 hydrogens. So I'm going to deal with the carbons and the hydrogens first. I see carbon doesn't have a problem, but hydrogen I need some more of. And so I'm going to change the coefficient of water to a 2, which will change this hydrogen to a 4, and it will change my oxygen total to 4. 2 from the carbon dioxide and now 2 from the water. So my carbons and my hydrogens are now balanced, so I can go back and look at oxygen, change its coefficient to a 2, which changes my oxygen to a 4, and the whole thing is balanced. So I want to react 3.5 grams of CH4, and I want to determine how many molecules of oxygen are needed. So we've done step 1 in our process. We wrote out and balanced the reaction. Step 2 is taking what I've been given and changing it to moles. So 3.5 grams of CH4 to moles must use the molar mass of CH4. So I take 4 hydrogens and 1 carbon and add them up, and that is 16.04 grams to 1 mole CH4. Step 3 in my process is to use the mole to mole ratio that I have in my balanced chemical reaction between what I've been given and what I want to go to. So I've been given CH4 and I want to go to oxygen. So I check my coefficients and see that CH4 has a coefficient of 1 and oxygen has a coefficient of 2. So therefore my mole ratio that I'm going to use is 1 mole of CH4 is equal to 2 moles of O2. The last step in the process is to go to the desired unit, which in this case was molecules. How do I get to molecules? Well, I need to use Avogadro's number. We know that 1 mole of oxygen is 6.022 times 10 to the 23rd molecules of oxygen. And then put it in your calculator. So 3.5 divided by 16.04 times 2 times 6.022 times 10 to the 23rd. And I get 2.62 times 10 to the 23rd. But I only need 2 sig figs, so 2.6 times 10 to the 23rd molecules O2 is my answer. And there was my page for my solution. Here's another example. We have 2.0 times 10 to the 21st formula units of magnesium phosphide reacted, wow, I'm missing a couple words here, reacted with sodium hydroxide to produce magnesium hydroxide and sodium phosphide. How many grams of sodium phosphide were produced? So how about you go ahead and hit pause, walk yourself through the process, and then hit play again, and you can watch me work through this. Okay. So I have magnesium phosphide with a formula of Mg3P2 reacting with sodium hydroxide, NaOH, to produce magnesium hydroxide, MgOH2, and sodium phosphide. If you're having trouble coming up with the correct formulas from the names of these ionic compounds, it might be worth going back and reviewing how to get from names to formulas. And then to balance, I see that I have 3 magnesiums on one side and only 1 on the other. So I'm going to change this to a 3. And 2 phosphorus on one side and only 2 on the other, so I'm going to change that to a 2. And then that leaves me with 6 sodiums and 6 hydroxides. So that should be your balanced chemical reaction, which was step 1. 2.0 times 10 to the 11th formula units. I'm going to abbreviate formula units as fun. Don't forget the N. Changes the meaning entirely. Of Mg3P2. And I know that I need to go from formula units to moles. And formula units, remember, is one of those Avogadro's numbers. So I'm going to use 6.022 times 10 to the 23rd fun of magnesium phosphide to 1 mole of magnesium phosphide. I'm in magnesium phosphide, but the question asked me for sodium phosphide. So I need to go to my balanced chemical reaction and see that my coefficient for magnesium phosphide was 1, and my coefficient for sodium phosphide was 2. So 1 mole of Mg3P2 is to 2 moles Na3P. And my last step is to convert to the desired unit. So 1 mole of Na3P. And I need the molar mass of sodium phosphide, so 3 sodiums, 22.99 times 3, plus 1 phosphorus, 30.97, gives me a molar mass of 99.94 grams. And then put it all in your calculator. So 2.0 times 10 to the 11th divided by 6.022 times 10 to the 23rd times 2 times 99.94. And I get 6.64 times 10 to the negative 11th, but I only need 2 sig figs. So my answer, and I'm going to write it up here so I have enough room, is 6.6 times 10 to the negative 11th grams of Na3P. There we go. So that's it for chapter 6. We covered a lot of material here, and so you'll really want to make sure that you follow up watching this video with actually engaging the material and doing some homework problems. So the homework problems are 1 through 42, 47 through 54, and 57 through 64. I'll see you in class.